Hello everyone, and welcome back to the Fluctus Channel. A railgun looks simple from the outside, but it represents one of the most demanding weapons ideas ever tested by the US Navy. Instead of using gunpowder, a railgun uses electricity. Two parallel conductive rails carry a massive current, creating force that pushes an armature and projectile forward at extreme speed. The attraction is obvious for warships. A ship could fire high-velocity projectiles without storing large amounts of explosive propellant while reaching targets far beyond the range of ordinary guns. At Naval Surface Warfare Center, Dahlgren Division in Virginia, the Office of Naval Research demonstrated this idea on land. Before any shot, engineers prepared the launcher, power system, test instrumentation, safety zones, and downrange sensors. The railgun needed a huge electrical pulse released in a fraction of a second to accelerate the round. Technicians checked capacitors, cables, cooling, barrel condition, projectile fit, data systems, and range clearance before authorizing safe fire. Once the command was given, the shot left the launcher with a violent flash, shock, and plume, proving that electricity alone could throw metal at hypersonic velocity. The Navy later demonstrated multi-shot salvos at Dahlgren. That was important because a single dramatic shot is not enough for a naval weapon. A future ship would need repeatable firing, controlled timing, manageable barrel wear, and reliable power recovery between rounds. The Navy described the railgun as capable of launching projectiles beyond 100 nautical miles at speeds exceeding Mach 6, but turning that into a sea-based weapon was much harder than proving it ashore. The main obstacle was power. A railgun needs pulsed electrical energy far beyond normal shipboard equipment. Warships already power radar, propulsion, communications, computers, weapons elevators, pumps, and defensive systems. Adding a railgun means storing energy, releasing it safely, cooling the launcher, absorbing vibration, protecting electronics, and recharging fast enough for combat. That is why the railgun stayed mostly on shore. Dahlgren could provide space, safety, power, and instruments that a ship at sea could not easily carry without major redesign. The test range, therefore, became a bridge between imagination and reality. Engineers could measure velocity, muzzle energy, wear, electromagnetic behavior, and projectile stability after every shot. The Navy proved that the concept could fire, and then fire again, but also showed why installation aboard an operational ship remained the hardest step. USS Zumwalt, DDG-1000, became the most discussed potential home for a railgun because it was built around integrated power. Unlike older destroyers, which separate propulsion and ship service electricity more traditionally, Zumwalt generates large amounts of electrical power and distributes it across the ship. That made it attractive for weapons that need electricity more than chemical propellant, including railguns and lasers. Zumwalt was designed as a stealthy destroyer with a tumble-home hull, composite deckhouse, advanced sensors, and a crew smaller than earlier ships of similar size. Its electric architecture was one reason analysts considered it the only practical U.S. surface combatant that might one day support a railgun without total redesign. Even then, the challenge would remain enormous. The ship would still need a launcher, cooling, magazines for projectiles, power conditioning equipment, fire control integration, structural support, and a reason to replace other weapons. During its live-fire missile exercise at Point Mugu, Zumwalt fired evolved Sea Sparrow missiles and SM-2 missiles as part of air defense testing. That event mattered because it showed the ship proving conventional combat systems while the railgun remained experimental. Modern naval defense cannot wait for weapons to mature. A destroyer must stop aircraft, missiles, drones, and surface threats with systems that work today. That is where weapons like CRAM fit the story. On ships such as USS Jackson, CRAM combines sensors and rolling airframe missiles in a compact defensive mount. Before firing, sailors prepare the launcher, verify safety arcs, connect the system to combat direction, and track the target. The launcher slews, locks, and fires a missile for quick reaction. Railguns promised speed and range, but CRAM demonstrated the practical reality of naval defense. A weapon must fit on a ship, connect to the combat system, and fire reliably when seconds matter. Japan has watched the same problem from a different strategic angle. As an island nation surrounded by busy sea lanes and close to missile threats from the region, Japan invests heavily in air defense, naval defense, ground systems, sensors, and reliable domestic defense manufacturing. The Japan Self-Defense Forces are defensive in name and mission, but their equipment must operate at a very high technical level. Because the country depends on sea control, airspace protection, and rapid response. Inside Japan's Ground Systems Research Center, under the Acquisition, Technology, and Logistics Agency, engineers research firearms, ammunition, vehicles, engineer equipment, personal gear, and CBRN defense technology. This is the kind of place where a future weapon begins as physics, materials, electronics, and testing before becoming field equipment. Japan's defense industry culture emphasizes careful evaluation, controlled trials, and reliability before adoption. Laser weapons are part of that direction. In demonstrations, Japanese directed energy systems are presented as tools for defeating drones or incoming threats with light rather than explosive ammunition. A laser weapon must detect the target, point accurately, hold the beam on one spot, manage heat, and keep power stable long enough to damage sensors, skin, control surfaces, or electronics. The process looks quiet compared with a missile launch, but the engineering behind it is demanding. Japan's railgun work has become even more significant. Like the US Navy system, it uses electromagnetic force to accelerate a projectile without gunpowder. Japan's ATLA began railgun research in the mid-2010s, and by October 2023, it announced a shipboard firing test of a railgun with cooperation from the Japan Maritime Self-Defense Force. Later reports connected the test effort to the research vessel JS Asuka, a destroyer-like trials ship used for naval experimentation. The Japanese concept is not simply about long-range bombardment. It is also linked to defense against air and surface threats, including fast missiles. High muzzle velocity means a projectile can reach a target quickly, and a solid projectile may cost less per shot than an interceptor missile if the system matures. That is why Japan's railgun program matters. It attempts to cross the gap that challenged the US Navy, moving from a land test into a practical shipboard firing environment. Japan's work shows that railgun technology is not dead yet. It is evolving through nations that see a need for faster, deeper magazines against missiles, aircraft, drones, and ships. The weapon is futuristic, but the requirements are practical. Fire when needed, survive at sea, and do the job better than existing systems. Railguns are only one branch of advanced weapon research. Lasers follow a different path, using concentrated light rather than electromagnetic rails to damage a target. One ambitious American effort was the YAL-1A airborne laser testbed, a modified Boeing 747 with a chemical laser intended to track and destroy ballistic missiles during their boost phase. The aircraft carried complex beam control equipment in its nose, along with sensors and laser systems inside the fuselage. The directed weapon laser system formed the heart of the concept, combining beam control, tracking, and fire control functions needed to put energy on a distant missile. During experiments, crews tested tracking, pointing, and engagement procedures. The idea was extraordinary. A large aircraft would patrol near a threat area, detect a launching missile, focus the beam on it, and weaken the missile structure before it could continue its flight. The challenge was equally extraordinary. The system was huge, expensive, chemically complex, and operationally difficult. It showed lasers could be used for missile defense experiments, but not every breakthrough becomes practical immediately. Still, the YAL-1A helped shape later work by providing lessons in beam control, atmospheric effects, tracking, and the enormous support requirements behind high-energy lasers. The Air Force Research Laboratory's work across the Century series of directed energy programs explored how lasers could move from giant testbeds toward more compact systems. A laser on an aircraft must deal with vibration, power limits, cooling, beam quality, targeting, and air turbulence. The smaller the platform, the harder those problems become. Testing on an AH-64 Apache pushed the idea into attack aviation. A helicopter-mounted laser must aim from a vibrating aircraft, hold energy on a target, and fit within tight limits for weight and power. The test did not turn every Apache into a laser gunship, but it showed how directed energy might one day support helicopters against drones, sensors, or light targets. The Navy has continued laser testing at sea. USS Portland LPD-27 successfully disabled an unmanned aerial vehicle with the Laser Weapons System demonstrator in the Pacific in 2020 then later used the same high-energy system against a static surface training target in the Gulf of Aden. The process is different from firing a missile. Operators detect the target, track it, point the beam, maintain dwell time, and let heat do the damage. Together, railguns and lasers show a Navy searching for cheaper shots, deeper magazines, and faster defensive reactions. Railguns strike with kinetic energy. Lasers strike with heat and light. Missiles like sea rams still protect ships today, while Zumwalt, Japanese test vessels, Apache experiments, and USS Portland point toward what may come next. The future of naval weapons depends on how power, sensors, cooling, crews, and platforms come together under real combat pressure in harsh sea conditions. That's the end of this video. I hope you enjoyed it. Make sure to subscribe to this channel so you don't miss any of our new content. See you next time.